This is Brennan with CIE 303, and what I'd like to look at here is a horizontal curve and derivations for how you would find these tangents, long chords, deflections, things like that. So right here in front of me I have this horizontal curve with station PI, intersection right here, BC beginning of curve, end curve VC, and let's say we have some delta angles through this arc length here. The circle of this arc length has a radius r, and we want to find out what's tangent, this line here, what is this long chord LC passing from BC to EC, what's the length of this curve segment that goes from BC to EC, and maybe what's the deflection of some station that might be some intermediate length along this length of the curve here, and it would form a line through BC and this point. And what's the deflection of that relative to this tangent angle here? Call it another delta. So first one's first, we can do the easiest first, the tangent. We can think of this as being, well, if we have this tangent coming off of the curve at BC, this automatically forms a right angle to the radius here. So if we made a right triangle that passed through PI, the center of the circle, we would have one triangle length of T, another triangle length of R. So this little interior angle here would be 1/2 delta, this total delta that we have. So tangent of this 1/2 delta is just going to be T over R, which if you rearrange this, T is R times tangent of 1/2 delta. So there is one down. Next one, which might be the next easiest, is this length of this arc curve that we have here. So if we thought about the total circumference of this entire arc of the curve, that would just be 2 pi times the radius of the circle. So we only want to look at this segment L, which is formed by only going through a portion of the total 360 degrees. We're just going through delta. So we're going to take this total circumference, and to find L, we're just going to take the proportion of this delta that we've gone through over the 360 degrees that we have times the whole circumference, 2 pi r. So there's a nice little formula for finding the length of the curve through this arc segment. It's just the proportion of how much angles have you turned through to form this arc over the entire circumference formed by a circle that would be traced by rotating this radius through a whole 360 degrees. So there's L. Next thing we might want to find is, what is this long chord here from BC out to EC? So this one gets a little bit trickier. We just have to find some more hidden right triangles. But if we form a line going straight through here to here, although my drawing isn't exactly to scale, this will actually cross through this line and form a right triangle here. So we've just formed this triangle here, which obviously we have a hypotenuse of the radius. We have some unknown distance here, which we're not really going to care about. But we know this distance here, it's just 1/2 of the LC that we're looking for. So 1/2 LC, if we were to write sine of this 1/2 delta, this interior angle here, same one we had before, sine of 1/2 delta, although we have a slightly different triangle, we now have an opposite side of 1/2 LC, and sine is just opposite over hypotenuse, so 1/2 LC over the radius will give us sine of this 1/2 delta. So rearranging, you'll have LC equals 2R sine of 1/2 delta. So that's where that one comes from. There's LC, and another thing that might throw you for a trick is, what if they just gave you this angle here? Why? Usually this is called I, but how could you go from relating this angle back to this whole delta right here? To get this one, we can think about, well, this I forms this if you line it up with this tangent line passing through PI, this I here plus this extra angle here, which I can just call theta, will form 180 degrees. They'll be right back to where this line meets again. So this angle theta here forms along with these two right angles, one at BC, one at EC, and this interior angle delta. They form a quadrilateral with side length R, another side length R, and then two more side lengths out here. So if we have a quadrilateral, the total angle of the interior angles should be 360 degrees. So if we add this up, we'll have delta plus 90 plus another 90 plus this theta, which we can relate to I. This should equal 360 degrees. So that means if we rearrange this to solve for theta, we'd have theta equals 180 degrees minus delta. But we can then say, well, this I plus this theta had to equal 180 degrees. So that means that if we were to say, well, this theta also then from this equation would equal 180 minus I. So if we then equate these two, we'll see that I and delta are interchangeable. They are the same angle. So given I, we can just say right off the bat that is this interior arc length delta. And last thing we might want to solve for is if we formed a line passing through this BC and some station length here, this would form an arc length, a semi-arc length from this total arc length L. So let's call this distance along this curve through here, let's call it A. And how could we relate this to the deflection angle that this would form through this tangent and this line from BC through this point? Let's call it capital A. We can think about what might be easier is what's the line, the deflection of the line, this BC through EC, this long chord that we calculated before. If we know this deflection of this line, delta long chord, then if we pass through some proportion of this to get to this whole LC, if we've only gone through this amount of it, we'll just be going through a fraction of this total delta LC. And so if we know this delta LC, we'll know this small one here. So delta LC can be formed by, well, if we have 1/2 delta here, again, we can go back to this right triangle. If this is 1/2 delta, this angle here is just 90 minus 1/2 delta. To get this angle inside here, this will be 90 minus 1/2 delta, or just 1/2 delta, and it pops up again. So if we wanted to find some smaller segment of this total arc length L with this deflection delta reference to this semi arc length A, this would just be, well, what's the proportion of A that we go over this total arc length L, and that will be the proportion of the delta curve for delta LC. So delta LC was just 1/2 delta. This will equal the delta that we go through for this smaller semi portion of this total delta LC. And so this will just be delta is, so your arc length that you pass through over the proportion of that arc length over the total length of the arc times 1/2 delta. So there's a few derivations of these formulas for horizontal curves.